Hi everybody, I'm the greatest living inventor, and today we are doing my invention, earthquake waveguide. Okay, so I'll write it down. Earthquake wave guide. Okay, so I did this already just now and I couldn't make it on time. It took more than an hour, so I need to really hurry up. I'm not explaining anything. I'm sorry. Everything that you don't know, like waveguide, you can read in Wikipedia. I'm sorry. And all the links will be in the video description as always. Divert earthquakes harmlessly far away from cities using coupled pendulums and thermal expansion. We will explain everything. I don't have time. This is a method for protecting a city from an earthquake. First of all, what causes most of the damage in an earthquake? This is a surface wave called Rayleigh wave. Okay, again, not explaining, we don't have time. This kind of wave can be guided in nature by a flat layer of rock, and then it's called lamb wave. You can see everything in Wikipedia. I'll give you the links. In fact, any wave can be guided, and we can steal the vibrating energy from one vibrating mass and transfer it away into another vibrating mass. We know this in electromagnetic waves and sound waves, and this siphon tube, so-called, is called a waveguide. Okay, you can see in Wikipedia waveguide. But lately, with smart materials, we see that we can manipulate seismic waves just like electromagnetic waves. Manipulate light to make invisibility cloak. Okay, you can see in Wikipedia seismic metamaterial. Seismic metamaterial. If you haven't heard of this cool new way to engineer existing materials into metamaterials, check it out here. Wikipedia, metamaterial cloaking. Okay, I don't have time. I will put it in the links in the description. Metamaterials and the Science of Invisibility by John Pendry from TEDx Imperial College, TEDx. And here in this TED lecture, he talks about manipulating the seismic wave by reshaping ordinary materials. Metamaterials matter, smart materials of future, by Niccolo McCaffrey from TEDx University of Luxembourg. Okay, so another YouTube video, I will put it in the description, by Niccolo McCaffrey. Metamaterials matter, smart material of future. Okay, so my idea is to take the dangerous Rayleigh wave and guide it away from the city, like a lightning rod takes the dangerous energy of the lightning, electromagnetic wave, and transfer it to the ground. Okay, so now we're talking about seismic lightning rod. Seismic Lightning. Rod. I'm sorry I don't have time, it's just, believe me, it's a long lecture. So it's in quote, unquote. Okay, because it's like a lightning rod. We know roughly where the waves will come from by looking at geology maps that show fault lines. United States Geological Survey, USGS. Okay, this is the United States Geological Survey. And I'll give you the link. For example, in this map by USGS from Wikipedia, San Andreas fault line. Okay, this is a picture from USGS. I will show it to you so you can pause the video and look. Okay, this is here. I hope it will focus. Okay, and especially look in San Francisco, you see, there are lightning bolts that go. I added the lightning bolts, were not in the original picture, I added them. So see in the San Francisco area, there are lightning bolts going away to the sea. We talk about it in the last part of the lecture, of the invention. But see, everywhere there is like red. Red is the danger, the fault line, and the yellow lightning bolts that I added are taking the danger away to the middle of nowhere, to the mountains or to somewhere else. Okay, they are taking it from the green areas that have population towards places without much population, like towards here where there is much less population. So the green are expanding urban areas. Can you see anything? Okay, so the green are cities. I can't figure out why sometimes it focuses and sometimes it doesn't. Okay, so now it's focused a bit. Okay, so you can see the green areas are the population, and then there is a red fault line, and then the yellow things, the yellow lightning is taking which is my invention, is taking away the energy towards places that are not inhibited, that they don't have much population. Like this is San Jose, a lot of population, and here there is much less population. Okay, so for example, in this map by the USGS from Wikipedia, San Andreas fault line, what you've seen just now, wherever there is a red-orange color, danger, next to a green color, dense population, city, we want to take the guide, to guide the red away from the green. Okay, take the danger, energy, away from the green population towards the wilderness. So I added the yellow lightning, to show in what direction we need to direct the energy away from dense population. Okay, how does this work? Coupled pendulums. Coupled pendulums. Okay, coupled pendulums are if you put two pendulums swinging back and forth, like one pendulum is swinging here and another is quiet here, not moving. After a while, this one will move and this one will not move. And after some more time, this one will move again and this one will not move. Okay, they are synchronizing alternately, moving the energy from this one to this one, to this one, to this one, and so forth. Until they will both be quiet because they will lose all the energy. But until then, this will shake, and then this will swing, and this will swing, and then this will swing, and then this will swing, and so on. Okay, so this is coupled pendulums. 12 minutes almost. Okay. If you've never seen coupled pendulums, I'm putting a few videos here. Coupled pendulums, 60 symbols. You will see it in the description. 60 symbols. Coupled pendulum minus the bagpipe music by Dan Russell. And the last one is how does it work, to the how does it work section. Okay, this is how does it work, coupled pendulums, but how does coupled pendulum work? You see in this video. Footnote, double pendulums are crazy by Minute Physics. Okay, so I'll put everything in the description. In our case, instead of two pendulums close to each other, we have two masses of land close to each other. Let's say this hill and the neighboring hill. Okay, so we have a hill and another hill. Okay, and let's say this is also covered in ground, and this is the ground level, and these are two hills or two mountains, and we have a tunnel. Okay, this is a tunnel that a road that goes all the way through, and here it comes out. Okay, this is the road that comes out, and actually there is a tunnel that you can imagine going through the mountain. Okay, so this is like this string. So the string here and the tunnel here, or the road, are making the same job. They are synchronizing this hill and this hill. Hill 1, hill 2. Okay, so in our case of two pendulums, in our case, instead of two pendulums close to each other, we have two masses of land close to each other. Let's say this hill and the neighboring hill. Suppose we can connect them with something, let's say a tunnel with a paved road inside that will convey the vibrations between them. Okay, it will pass the vibrations from this hill to this hill. like in the demos you see with the pendulums. What will happen with the two hills? The first one will start to shake because the earthquake hits it first. And normally, without the tunnel, it will transfer the energy to all its neighboring hills equally. But once we have the tunnel, then almost all the vibrations move fast into the second hill, and then back and forth. Because the walls of the tunnel are more solid than the surrounding ground. And it's easier for the vibrations to travel inside a solid medium. Okay, so we want something like this, or like this, but in the ground. Okay, so again, when I'm saying lightning rod, I mean something that transfer here the physical vibrations. I'm not talking about electromagnetic wave. It's just a metaphor for something that takes the energy, the energy of the wave from one place to from a place of danger, the building, to a place that it's not danger, deep in the ground. In the case of lightning rod. And in the case of the light wave, I don't remember the name of the invention, but the waveguide of the earthquake, it means taking the vibrations of the earthquake from the city where it's dangerous, the seismic vibrations, the actual vibrations of the earth, to another place which is far away in the wilderness. Okay, so I'm saying lightning rod, but it's a metaphor. Okay, so what materials do we need? Okay, so this is our next subject. So what we need is something like a coil spring that can conduct the vibration from one block of area on the map with many people into another neighboring block of fewer people. Let's say 100 kilometers away. Okay, something with almost no people, or ideally no people, like the middle of wilderness. Because there is a lot of energy, like a national park. Because there is a lot of energy to transfer, I suggest our spring will actually be a straight metal bar. I think steel is the best. Where do we get 100 kilometer long steel bar? We need to cast the metal on the spot. Okay. We will not use a steel bar, but I'm explaining how we develop the idea. We first dig a long ditch, 100 kilometer long. Okay, so we have the ground. Okay, and we have this is a building. Like this is the city. And we have here the country. Okay, so, and we want to move the, and here are a lot of people. And we want to move the energy from here to here. Okay, so we take our most naive way is to take a bar of steel. Okay, this is a steel bar. And if we look from the side, then, okay, this is a look from the side, this is a look from the end. Look from view from end side. So we have the ground. And we are digging a ditch. And here we cast the iron, the steel, sorry, the steel. Okay, so we cast here steel. We have steel and we cast it, and we have the iron bar here. Okay, you understand more or less? Okay, so because there is a lot of energy to transfer, I suggest our spring will actually be a straight metal bar. I think steel is the best. Where do we get 100 kilometers long steel bar? We need to cast the metal on the spot. We first dig a long ditch, 100 kilometers long. Okay, so here is a ditch. This is all happening inside the ditch. Okay, all this is a ditch. We first dig a long ditch, 100 kilometers long, because we need the steel bar to be buried underground in depth where this kind of waves, Rayleigh waves, travel. I couldn't find this depth anywhere, but from this article, Rayleigh waves from small explosions, I will put it in the links, by Dobrin MB, Simon RF, and Lawrence PL, 1951. This is appeared in the, published in the Transactions American Geophysical Union, 32, 6 volume, page 822. Okay, so I'll give you the link. I've seen it in SciHub. I'll give you a legal link. I guesstimate about, we need to put the steel bar buried under, from this article, I guesstimate that we need about 20 feet deep down, which is about 6 meters. Okay, so here, this is about 6 meters, and the length, as we said, is about 100 kilometers. Okay, so 100,000 meters, and the deepness is 6 meters. Like they say 6 feet under, but 6 meters under, so it's more. Okay, the wave will want, in quote unquote, the wave will want to travel through the bar because it travels faster, which means more easily there. Now I'm reading from Wikipedia. Rayleigh waves have a speed slightly less than shear waves by a factor dependent on the elastic constants of the material. The typical speed of Rayleigh waves in metals is of order of 2 to 5 kilometers per second. The typical Rayleigh speed in the ground is of order of 50 to 300 meters per second. Okay, you can read this in Wikipedia in Rayleigh wave. Okay, so you see that it's traveling instead of 300 meters per second, or about, let's say if it was 200 meters per second, and this is like 4 kilometers per second, so it's 4,000. So it's 4,000 divided by 200. Okay, so it's 20 times. Okay, it travels 20 times faster inside the steel bar. Okay, if I'm not mistaken. Okay, so the Golden Gate Bridge. So now I'm talking about how it's not economical to use steel, and we want to use cement. Okay, the Golden Gate Bridge contains about, okay, the Golden Gate Bridge, I'm sure you know it, in San Francisco. Golden Gate Bridge. So the Golden Gate Bridge, now I'm throwing a lot of numbers. It's just to mean, I'm just meaning to say that we don't want steel, we want concrete. You don't need to worry about the numbers. They are just the final bottom line is that we don't want steel bar, we want a concrete bar. Reinforced concrete. Okay. The Golden Gate Bridge contains about 88,000 tons of, like American tons, of steel, which is 75,000 metric tons of steel, like European. 75,000 metric tons of steel. 1 metric ton equals 1,000 kilograms. So the Golden Gate Bridge weight is 75 million kilograms. So if our steel bar is shaped like a cylinder, okay, cylinder like a rod, of 100 kilometer height, which is 100,000 meters, and the radius, okay, it's lying down, so it's the height is actually the length. So and the radius of 1 meter from the side, if we look here, it's 1 meter radius. Its volume would be pi times radius squared times height. Volume would be 3.14, which is pi, times 1. 1 squared is still 1, which is the radius, times 100,000, which is the length or the height. If it's standing, it's the height. So it's 314,000 cubic meters of steel. The weight of 1 cubic meter of steel is the weight of 1 cubic meter of steel is 7,850 kilograms. So a steel bar would have a weight of 2,464,900,000 kilograms. So we need almost 33 Golden Gate bridges for one steel bar. But in a bridge we have a limiting constraint, which is the weight, because it needs to hold its heavy weight above the water, so the chips can pass below the bridge. Here we do not have this limiting constraint, so we can use reinforced concrete, which is concrete with very thin steel bars inside it. Okay, reinforced. So instead of a steel bar, we use reinforced concrete, which is like concrete. Imagine this is a concrete slab, and it has metal inside it. Okay, it's like I will draw it in another color, but it's actually, it should be, this should be gray. It's a concrete, it's gray, and the metal rods should be also gray, or like even black. So or like a little reddish if they are rusty. So let's do them in red. Okay, so I'm drawing this in red. So it has metal rods inside it. I drew one, but it has many metal rods inside it. Okay, so this is steel metal rods. Okay, but the metal rods, if you look from the side, if we look at this from this side of the concrete, so if this is the concrete, then most of the area, side view, most of the area is concrete, and just a little bit of steel rods here and there. Okay, but most of the area is concrete. So it's about 6%. Okay, only 6% is metal. Inside the concrete there is only 6% metal. Okay, most of it is concrete. Let's see what's the time, 32 minutes, and I'm in the 6th page, so I need to hurry. Okay, so here we do not have this limiting constraint, so we can put something very heavy and the earth will support it, not like a bridge that needs to be in the air. This is on the ground, this is inside the ground, just lying there. So we can use reinforced concrete, which is concrete with very thin steel bars inside it, and it has compressive strength, strong against pushing, and because of the thin metal bars inside it, it's also strong against tensile strength, pulling, strong against pulling. So how much steel do we need now? The relative cross-sectional area of steel required for typical reinforced concrete is usually quite small and varies from 1% for most beams and slabs to 6% for some columns. Okay, if it's a column that needs to hold a skyscraper or something, no, that's with the steel. But if it's a column that needs to hold the building, then it's 6%. So we need the stronger one, the 6%. Okay, so you can see in Wikipedia, reinforced concrete. So let's go with 6%. Then we need almost 2 Golden Gate bridges, okay, and not 33, just 2 golden bridges of the amount of steel that we need, the red color. Okay, 6% metal. So the metal of only 2 Golden Gate bridges. Of course, we also need concrete, but concrete is a lot cheaper than steel. According to Les McLean from Quora, steel costs 1 cubic meter would cost approximately $3,905 US. Okay, if we have a box of metal, of steel, and we have how much does it, of 1 meter side, how much does it cost? $3,905 US. So about $4,000. This is from Quora. What is the cost of 1 cubic meter of low carbon steel? And according to Kent Aldershoff from Quora, 1 cubic meter of concrete would cost about $78.5 US dollars, so about $80, 80. So this is from Quora, how much the cost of concrete per cubic meter. So the 95% of the mass, okay, except this 5%, about 5%, we have 95% of the mass of this thing, of this reinforced concrete rod, is made from concrete, which is 50 times, okay, 50 times cheaper than steel. So instead of 4,000 for a cube, it's $80 for cube. Okay, so it's 50 times cheaper. So I think the best way is to dig one long 100 kilometers big ditch for the concrete, and running alongside it one furrow for each steel rod that we want. So for each one like this, we make a little furrow, a little ditch. Okay. So we have little ditches here and here and so on. And here we have the making the rods. And then we roll them towards the hole, and we spill. Now it's not metal, it's not steel, it's concrete. Okay, so we put some concrete, and then we roll in a metal rod, and some more concrete, and more metal, another metal rod. Okay, and so on. And we make this structure of reinforced concrete, but on a very large scale. So I think the best way is to dig one long 100 kilometers big ditch for the concrete, and running alongside it one furrow for each steel rod that we want, then cast the steel rods and let them harden. After we have steel rods ready, after we have the steel rods ready, we cast simultaneously all along the ditch some concrete, and then lower a rod simultaneously into the mix, and repeat this concrete rod, etc. Okay, now cutting off the energy so it doesn't return back. Cutting off the energy so that it doesn't return back. Okay, what do I mean? You remember that I said that if there were two hills, okay, we had two hills, and we said that this hill would shake, and then this hill will shake, and then this hill would shake, and then this hill will shake, and we don't want this. This is where the people are, this is where the empty nature, but no people are, and we want this to pass all the energy to this, and only this shake, and then cut the connection so the shaking doesn't come back. Okay, so so cutting off the energy so it doesn't return back. But remember, we said the energy will travel back and forth between the two neighboring hills or blocks of land, and we want to send the energy away with a one-way ticket and disperse there. We don't want it to come back. So what we need is to engage at the beginning. Normally we have 45 seconds or so in the beginning of the earthquake. Okay, you can see this in Wikipedia, earthquake warning system. Okay, so we need something that with the switch of a button will connect our lightning rod to the ground, and with a flick of a button will disconnect once the energy moved away from the city. It also must be very strong against pushing, ideally as strong as the concrete and the steel that we are using, because the vibrations, the pushes, sorry, it's on this side, the pushes will pass through this thing. Okay, so what will be the connecting element? Okay, so now we are talking about thermal expansion. Think of gaps in train railway. Thermal expansion. Think of gaps in train railway. Okay, so thermal expansion. In Wikipedia you can see expansion joint. Expansion joint. Okay. Why bridges move? By practical engineering. In parentheses, this effect can be seen in minute 4 of the video, close parentheses. So I'm giving you a link to a video. Why bridges move? By practical engineering. Okay. So in long straight sections of the lightning rod, we need to make gaps, so that our one lightning rod is built from a series of many lightning rods that almost touch. Okay, so here is a gap, and here is a gap, and here is a gap, okay, and so on. Okay, gap. That almost touch. When we make the lightning rod, this whole thing, before we bury it in the ground, we need to connect electrodes to both sides of each section, so that we can run electricity through the thin steel rods inside the concrete. Okay, so we have an electrode here. Okay, and an electrode here. And this is like the plus, and this is the minus, and we put electricity through the red, through the metal, okay, through the metal rods of each section that we want. Like we can, we also have electrodes to here, and so on. Okay, so we activate each of them separately. Well, to be honest, we activate everyone at the same time, but each of them, each of the sections has its own electrodes. So when we make the lightning rod, before we bury it in the ground, we need to connect electrodes to both sides of each section. Okay, so here we have like a battery. Okay, it's not a battery, but it's like a battery, a power source. Okay. to both sides of each section so that we can run electricity through the thin metal rods inside the concrete. This will cause the steel to heat up and expand, and also the concrete will expand because it takes heat from the steel, and concrete has almost the same thermal expansion as steel. Okay, this is why they work well in reinforced concrete, because otherwise it will break when it's heating, but they expand almost the same. So when we activate the rod, all its parts are touching and connected, so they are pressed hard against each other and they transfer the vibrations. When the energy was transferred far away, okay, to here, we quickly disconnect the electricity. Okay, there is no longer electricity here, and then they separate again. When the energy was transferred far away, we quickly disconnect the electricity and the rods cool down and shorten. They are separated by gaps, and the energy cannot return. Okay, the energy can come to here, but it cannot go back to here. Okay, so 46 minutes, excellent. So now we are in page 9. PS, okay, like I remembered it later, waves under the sea. Okay, so I'm erasing this. Okay, so now we are talking about waves. Of course, we are talking about seismic waves. Let's make sure that we understand it. Seismic waves under waves under the sea. Okay, you might ask yourself about the two lightning rods nearest to San Francisco. Remember, I told you that they go into the sea in the picture, that are located in the sea. How can we cast steel and concrete on the bottom of the sea? In the ditch, we are making a ditch and we want to cast and let it harden. But how do we do this under the sea? There are water there, like high pressure water. So for drilling, we can use all the oil and gas rigs that are pumping carbon into the air from offshore drilling. Instead of killing people, let's use them to save people. Rayleigh wave cannot travel in the ocean, but there is something similar called a Scholte wave. Okay, Scholte wave. Okay, so you can see in Wikipedia Scholte wave, which can travel along the border between sand on the seafloor and water. Okay, so we have like we have San Francisco. Okay, this is San Francisco. I don't know how the iconic buildings of San Francisco look, sorry. But let's say this is San Francisco. And here we have the sea. And we want to take the energy from the city to the bottom of the ocean where there is sand. Okay, this is sand. And of course this is water. Okay, and this is ground, earth. Okay, so maybe we can, I'm sorry, Rayleigh wave cannot travel in the ocean, but there is something similar called Schloter wave, which can travel along the border between the sand on the seafloor and the water. Maybe we can translate the energy from one kind of seismic wave, Rayleigh, into another kind of seismic wave, Scholte. I think that the answer is yes, because we see an analog to this in the physical phenomenon of Wilberforce pendulum. Okay, so I'm not explaining, although it's very cool. Wilberforce pendulum. Okay, it's not the name of a force, it's the name of the guy, Wilberforce, and it's like it's translating this movement up and down, bobbing movement to a rotating movement. Okay, so you should see it in the videos. See a nice video here, PHMECE demo 70041A V0241, sorry, that's the name of the video. Wilberforce pendulum by UniServe Science video. Okay, I'll put the link in the description. And also a video here, Wilberforce pendulum by Berkeley lecture demos. Okay, it looks like nature is happy to trade the energy in one oscillator with the energy in another oscillator. Okay, it's like instead of bobbing like this, it stops and then do this, and then stops doing this and translate back to this until it's tired. But it's doing this back and forth like the hills. So it looks like nature is happy to trade the energy in any oscillator with the energy of any other oscillator. So to build underwater is of course more challenging. We would need to make a tent of air for which would be upside down, just like a diver's bell. Okay, so a diver's bell is something that you take like a shape of a bell. Okay, this is like a bell, and you put it inside the water, and of course it's without this thing. It's not a real bell. There are seats here that the divers can sit on, and they have oxygen here, and you put it down, and the people can breathe. Okay, so it's something like this. And there is also, if you make it from something, diving bell. Okay, and this is a diving tent, which is the same, but from fabric, from material that is soft, like flexible, diving tent. Okay, so you can see in Wikipedia diving bell. I think we should build this at first from some soft material, like the balloon that you see here. Michael Lombardi, inventions enable diving to new depths. Net Geo Live by National Geographic. You can skip over the first 10 minutes. That's my remark. Okay, it's in YouTube. I'll give you the link. Michael Lombardi, inventions enable diving to new depths. Net Geo Live by National Geographic. So we can connect this kind of balloons and anchor them to the sea floor. Okay, so we make a balloon, but right on the sand. Okay, so the balloon would be here. Okay, we anchor it. So we have air here. And here we anchor this to poles like a tent. And we have balloons all the way, or tents. We have we connect them. Okay, so we have a tent here and a tent here and so on. And we connect them. So, so we can connect this kind of balloons and anchor them to the sea floor and make a tunnel of air where people, or better yet robots, because it's dangerous, can work and cure. Cure, it means to make hard, to make the concrete or make the steel hard. It's called to cure. Like cure a disease, but it's not curing a disease. It's not like making a sick person better. It's like making concrete or steel hard. So it's called cure. So so the robots can cure, can work and cure a half pipe of concrete. Basically, do what we did on ground, but under this long tent. The problem is that we are limited to how long a tent we manage to stitch together. For this, we need to make a process which is not all in once, but instead it's an assembly line. Okay, so assembly line, like you see in the movie, the amazing movie of Charlie Chaplin, Modern Times, where he is working on the assembly line and running and has to get back. So, assembly line. Okay, so we do an assembly line of tents. We make this part and then we make this part and so on. We have a tent of air, that covers the length of 2 kilometers, units 1 and 2. And under its cover, the robots are curing the first kilometer, making hard the first kilometer of the road. And after they move on to work on the second kilometer, meanwhile, the first kilometer is hard enough to be exposed to water. And now we advance the tent of air forward to cover the next 2 units, unit 2 and 3, and so on. Okay, so that was my invention. It's 1 hour exactly. So I hope it was clear, and I'll see you in my next invention. So thank you very much. Goodbye. Thank you.